Okay, here we go with section 2.2. We are still focusing on functions, the graphing of functions. We already, at the end of 2.1, we tackled symmetry. Now again, we're going to do just one symmetry test. And we have, our symmetry test is going to be that we plug in a negative x into whatever function we're working with. If we plug in that negative x and nothing happens, nothing changes, the sign on each term remains the same, then in that case we have symmetry, it's symmetric about the y-axis. It's an even function, symmetric about the y-axis. Our example from, one of our examples from our previous page with the parent functions is our parent quadratic function. F of x equals x squared, because if I plug in that negative x and I square a negative x, negative times a negative is a positive, nothing changes. So that's an example of an even function. Then we have our odd function. We know we have an odd function if we plug in that negative x and every term has a sign change. So we get out the opposite of what we started with. If it's an odd function, it's symmetric about the origin. And we know from our parent function page, one of our examples of an odd function was our cubic function. F of x equals x cubed. If we plug in that negative x and we cube a negative x, a negative times a negative times a negative is still a negative. So we have the opposite of what we started with. Negative x cubed instead of positive x cubed. So that's what happens when we have odd symmetry. Symmetry about the origin, O and O. Odd functions symmetric about the origin, even functions then are the y-axis. Now what if we plug in our negative x and some terms change sign, some terms don't change sign? Well, in that case we say we have no predictable symmetry. You don't say there's no symmetry, because there may be, it's just not y-axis symmetry or origin symmetry. We have no predictable symmetry. Well, what's an example of that? Let's say, let me pick a different color altogether. Let's say that we have, let's go back up here. Let's say we have a squared function, but not the parent function. Let's say we have g of x is x squared plus 5. Well, we've moved it up. That's still fine. That's going to be even. G of x, sorry. I'm having a hard time today. Negative x equals, I square that, nothing changes, x squared plus 5, still even. Still even. We just shifted it up. Now we are up here. So that is not an example of neither. Sorry, guys. How about, though, let's do this one. How about if we take f of x equals x to the 4th minus 7x cubed? So we've got two terms here. This is a 4th degree polynomial. I don't have a shape for the parent function for that yet. We'll talk about that later this semester, but I haven't shown you anything 4th degree, x to the 4th. What happens if we plug in a negative x? Well, let's look at it. If I plug in a negative x, I have a negative x to the 4th minus 7 times a negative x cubed. Well, even exponents, those negatives even out. Negative times a negative is a positive, negative times a negative is a positive. This term stays exactly like it is, doesn't change. This term, however, negative x cubed, 3 negatives, negative times a negative is a positive, times a negative is a negative. So I have a negative x cubed times a negative 7, that becomes plus 7x cubed. And this is the one where I have, okay, this stays the same. This one changes sign. Stays the same, changes sign. This one started positive. This second term started negative. It became positive. So if some terms change sign, we don't have predictable symmetry. So when I plug in that negative x and some terms change, and some can be just one term. If anything changes, and not everything changes, it's not predictable symmetry. Okay, let's practice our even-odd functions. Even, odd, or neither, and give it symmetry. Well, this first one, I see that I've got two terms, and they both have an odd exponent because x is just x to the first power, right? They both have an odd exponent. So if I plug in a negative x, well, multiply it 3 times, that changes to a negative x cubed. This is just minus x. Both terms change sign. Both exponents were odd. Both terms change sign. This is an odd function with origin symmetry. This is an odd function with origin symmetry. Now, notice that I said we had odd exponents. Both of our terms have odd exponents. We ended up with an odd function. What do you think? We've got two of these left, g of x and h of x. Which one do you think might be an even function? Well, look down here. H of x has even exponents. 2 and 4 are both even exponents. If I plug in a negative x and then I raise it to an even power, those negatives are going to pair up and go away. So negative x times negative x is a positive x squared. Negative x times itself 4 times, those negatives pair up, and it becomes a positive x to the 4th. So this stays minus x to the 4th. This is the same as what I started with. So this is an even function, which means I have y-axis symmetry. Now g of x is a little different, right? G of x has an even exponent and an odd exponent. So what do you think is going to happen? Well, my even exponent, not going to change sign. My odd exponent is going to change sign. If I plug in that negative x, when I square it, nothing happens. When it's just x to negative x, that is definitely a change. So stays the same, changes sign. Got to be all or nothing for even or odd. So this one comes out to be neither even nor odd, which means I have no predictable symmetry. No symmetry, no predictable symmetry. Now, notice that for the two terms on each of these functions, none of them was a constant. A constant like this plus 5 here, a constant is constant. Constant means unchanging. That constant's never going to change signs. So a constant is fine with an even function. It's going to mess us up. We can't have an odd function with a constant because that constant is not going to change signs. Okay, let's tackle the next bit. Now, I just want to remind you that from 2-1 we have our parent function. We have our parent function sheet. Make sure you have that kind of handy as you work through these next 3 sections. Behavior of functions. You've got different types of behavior of your functions. Our behavior of our functions tell me what my function value, my y value, is doing, if it's increasing, decreasing, going up, going down, or if it is constant, if it's flat. Now, to figure out behavior of functions, I'm going to read my graph along the x-axis. I read it from left to right, just like I would be reading a book. The behavior I'm interested in tells me what my function value is doing. Remember, your function value is your y value. Is your y value going up? Is it going down? Or is it staying flat? Increasing, decreasing, or constant? Now, when I am reading this behavior, I also am looking for relative maxima, peaks, or minima, valleys, where a function turns. When I have a turn, that means, like for example, I may be increasing, 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 and then I turn. So I've got a peak, relative maxima. I am increasing here, I am decreasing there. That's what I'm talking about with behavior for my functions. Okay, let's do an example of this. Keep this all handy so that you can refer to it while we talk about our graph. Now I noticed a couple of things right away. I noticed that my graph has arrows on the end. It's going to keep going down forever. I'm interested in my function value. My function value is my y value. So I'm asking myself, what is y doing? What's my function value doing? That's my question. While I'm asking that question, I'm reading along the x-axis, and my answers are going to be intervals on the x-axis. Now, my answers need to include all of the x-axis that's included in my function, so I need to think about my domain. And I see that because my domain, this function is going out, 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 my domain is going to be all real numbers. So when I answer with intervals on the x-axis, my intervals need to end up including all real numbers. Okay, now the arrows are going down, but that just tells me that my graph continues. I'm reading my graph x-axis left to right like I would read a book. So I start over here at negative infinity and I am moving toward the right, from left to right. As I'm moving toward the right, my graph is climbing. My y value is climbing, climbing, climbing. It is increasing, it is climbing until it gets to this relative minima point. Right here we've got a change. But from the x values, negative infinity all the way to negative 4, we are increasing. So we are increasing from negative infinity to negative 4. And then we got a point of change, so I don't include that. Do you see if I'm increasing anywhere else? Well, I gave you a cheat sheet, didn't I? So I'm increasing here. Right here to here, because those are points of change, my graph is increasing. It's going up. So on the x-axis from 4 to 6, my graph is increasing from positive 4 to positive 6. Again, I have changes at 4 and 6. I'm not going to include those. All right, so let's talk about where we are decreasing. My graph is falling. Again, I'm reading the x-axis from left to right. As I'm reading across the x-axis from left to right, the behavior of my graph is going down, 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 down for this part of the x-axis from negative 4 to 0. I see that my function is decreasing. The function value, the y value, is decreasing from negative 4 to 0. That's the interval on the x-axis that the graph is falling. Is it falling anywhere else? Well, yeah, because I gave you a cheat sheet again. After I get to this point at x is 6, my graph is going down forever. So this part of the x-axis, this part of the domain, from 6 to positive infinity, my graph is falling. So I've included almost all of my domain. What have I left out? Well, I've left out this bit right here from where x is 0 to x is 4, where the graph is just flat. That's constant. So it is constant on the interval on the x-axis from 0 to 6. The y value is constant at whatever this positive value is. It could be 1, it could be 100, it could be 1,000. We don't have any markings on our y-axis, but it's constant on the interval in the domain 0 to 4, not 6. Wow, I'm so glad we caught that. So here is the danger of me sitting in my office without you guys making these videos. I will make mistakes, and there's no one here to call me on it and to stop me. So if you notice a mistake, please let me know. in Canvas or email or somehow so that I can at least make a note of it later. All right, so that's how we read behavior of the graph. We ask ourselves what y is doing, and we read the x-axis so that we talk about intervals on the domain where our function is increasing, decreasing, or constant. Okay, let's practice this. I was going to look ahead. We've got one big thing to practice with this, and then we move on to another bit of a different topic. But you're going to notice that everything is tying in together, right? We're not moving on completely from one topic to the next. We're talking about graphing and functions and movement on that graph and describing those graphs. Okay. So remember that when I'm interested in increasing, decreasing, and constant, I'm reading along the x-axis, talking about my function value. I need to think about my domain first, and I see that this function has arrows on both ends, so it's moving out. My domain is going to be all real numbers. What about the range? Is my range all real numbers? Well, this one goes up forever, so I don't have an upper limit, but I do have a lower limit. The lowest y value my graph gets to is -4. So I have a lower limit at -4, upper limit, nope, no upper limit, goes to positive infinity. Other things that I'm asked for x-intercepts, that's a good one. X-intercepts, we cross the x-axis here at 1 and 7. I'm going to give those x-intercepts as ordered pairs. X-intercepts happen where y is 0. I can have as many x-intercepts as I want. If it's a function, I will only ever have one y-intercept. Y-intercepts happen where x is 0. There's my y-intercept. X is 0, y is 4. Now, behavior for our graph. Where is my function increasing, decreasing, or constant? So let's start with increasing. I see that from this turning point, right here I have a turning point. From this turning point, my graph is going up. This turning point happens where x is 4, and then my graph goes up for the rest of forever. So my graph is increasing on the interval on the domain from 4 to positive infinity. Now let's look to see where the interval on my domain is that my graph is decreasing. And I see that my y value falls here. We've got this point of change. We also have a point of change here where x is 0. So from where x is 0 to where x is 4, that interval on the domain, my function value is decreasing. So from 0 to 4, my function value is decreasing. This is the interval on the domain. Decreasing describes what the graph is doing. Then finally, where is my graph? Constant. And my graph is constant. Whoops, excuse me, I'm throwing stuff now. That was not intentional. My graph is constant where it's flat going across horizontally. And if I'm reading my domain from left to right, from negative infinity all the way over, this entire part of my domain is where the graph is constant. So from negative infinity all the way to 0 on the domain, my graph is constant, and at 0 we have a point of change. Those points of change are not included. Now, we might have a graph that is never constant, and if it's never constant, I write NA, not applicable. If it's never increasing, I write NA, not applicable. I don't ever leave one of those questions blank. Okay, relative minimum. A minimum is a low point or a valley. A relative minimum, it's relative because it may not be the lowest point of the graph, but we've got a dip, we've got a valley. In this case, our minimum value is the lowest point. It's the absolute minimum. The number at which my function has a minimum is at x equals 4. Right there, where x equals 4, we have the minimum value of the graph. The minimum value, that relative minimum of f, is the y value -4. So that is -4. Another way to say that is f of 4 equals -4. But notice how the questions are worded. The number at which the function has a minimum, well, that happens where x is 4. What is the minimum? The minimum value is -4. And then we've got another missing value here, f of -3. Well, f of x, so x is replaced by -3. -3 is here. There's my function. The function value is 4 there. The values for which f of x is -2. Now notice I don't know x. This is my function value. That's my y value. So I'm looking for the x values where y is -2. So y is -2 here. Oh look, y is -2 here and there. I've got two places where I have x values that the y value is -2. It happens where x is 2 and x is 6. So the answer to that one, x is 2, x is 6. And then I have a symmetry question. Is my function even, odd, or neither? Am I symmetric about the y-axis? Am I symmetric about the origin? Or neither one of those? Well, I can't fold it on the y-axis and have the sides match. It don't have a twist in the middle, so it's not symmetric about the origin, which means I have neither type of symmetry. Now remember, you have control of this lecture. You can pause, you can rewind. I encourage you to answer all the questions, get it down, maybe consider going back to re-listen and talk your way through it again to make sure you understand what we're doing. Our next type of function that we're interested in are our piecewise defined functions. We're going to do a couple of those, and then we're going to talk about difference quotient. So we have two more topics to cover in this section. Sections 2.1 and 2.2 have a lot of information. Things will kind of slow down a little bit as we move through this semester, but getting everyone on the same page and everyone filled in takes a lot of work here at the beginning. Piecewise defined function is a function where different rules define different regions of the domain. Our function is pieced together from different parts of the domain. My most basic piecewise function is our absolute value function. Now we know from our parent function sheet, you can go grab that if you want to, you know the shape of our absolute value function. So let's talk about our absolute value function. Our absolute value function says that no matter what I plug in for x, it comes out positive, right? So if I want to write this absolute value function as a piecewise defined function, I can rewrite it as f of x is x for the part of my domain where x is greater than or equal to 0. And it's negative x for the part of my domain where x is less than 0. So I have two rules for my piecewise defined function. For the first rule, I'm interested in the part of my domain x values greater than or equal to 0. That's this part of my domain, right? So let's set up a chart over here. X values greater than or equal to 0. I'm interested in the rule f of x equals x. So I need to pick values that fit here. I'm going to pick 0 because that's my dividing point. And I'm going to pick something that's greater than 0. I'm going to pick a 2. I could also pick a 3, but I know I'm going to have a straight line because I know what to expect. If I plug in 0, I get out 0. If I plug in 2, I get out 2. If I plug in 3, I get out 3. So this piece of my function looks like this. Okay, then the other piece of my function, that second rule for my function, is for the piece of the domain x values less than 0. And notice that I included 0 in one piece but not the other because that makes it a function. When that happens, I plug in x, I get out the opposite of x. So I'm going to have to use 0 here so I know where I stop or start, but I'm going to put these little wiggly lines to show that that's an open circle. And then I'm going to pick something over here. Well, these are all negatives, so let's do a -1 and maybe a -3. If I plug in 0, the opposite of 0 is still 0. 0 is not positive or negative, it's neutral. If I plug in -1, the opposite of -1 is 1. Plug in -3, the opposite of -3 is 3. I have ordered pairs to graph. Now I know that I'm going to go here, but it's going to be open circle. -1, 1 is a point on my graph. -3, 3 is a point on my graph, and this piece of my function continues forever in that direction. that's how my parent function, absolute value, can be written as a piecewise defined function. We've got two different pieces of our graph. Okay, let's do one that's a little bit more interesting. We've still just got two pieces of this function as it's given to us and defined. The first piece is a constant. -3 is just a constant. The second piece, that's going to be linear. 2x plus 4, if I were to graph that, that's a line. And what do I see about my domain? I see that my domain is split at 0, and 0 is not included in either piece. Up here I included 0 in this first piece. 0 is left out here. So my domain for this function is everything but 0. -infinity to 0 or 0 to positive infinity. I'm leaving out that value 0. It's not included in either piece. Now, when I think about what this looks like, -3 is a constant. Constant function is flat, straight across line. So it doesn't matter what I plug in, my y value is going to be -3. This is true for x values less than 0. No matter what I do, I get out -3. Now, we need to pick some x values less than 0 that are on this piece of my graph. Let's just do what we did. Let's do -1, -3. You know what? We've got to go all the way to 0 though. It's not included, but we got to think about it. Now, no matter what I plug in for x, I get out -3. -3, -3, -3. This one's not included, but it's where I have to go to. So for this piece of my graph, everything over here, my y value is going to stay at -3. So -1, -2, -3, all the way up to, but not including, where x is 0. That's my stopping place or my starting place, depending. This is this piece, this first rule for my function. The second piece, the second rule for my function is 2x plus 4. That happens where my domain, x greater than 0, g of x, that should be g of x, not f of x. Doesn't make a big difference, but we'll try to keep it straight. G of x is 2x plus 4. Okay, now we're only interested in this piece of the domain. We've got to consider 0, even though it's not going to be a filled in circle. It's going to be an open circle again. Then I got to pick something greater than 0. I know this is going to be a straight line. It's going to be linear, so I really only need one point to connect. It doesn't matter. I could put 10 or 100 or 1,000 if I wanted to, but let's pick something easy to graph. Let's just pick 2. Okay, if x is 0, if I plug in 0 for x, 2 times 0 is 0 plus 4. If I plug in 2, 2 times 2 is 4 plus 4 is 8. That may be kind of high. Let's go ahead and do 1 to make it a little easier. 2 times 1 is 2 plus 4 is 6. Those are ordered pairs that fall on my graph. This is also on my graph, but it's as my limit. It's as my starting place as an open circle because it's not included in that piece of the domain. If x could be 0, y would be 4. 1, 2, 3, 4. Open circle. And then my slope is a positive 2 for this line, so if x is 1, y would be 6, which would be right about there. X is 2, y would be 8, and it just keeps going super steep up forever. So my piecewise defined function has two separate pieces for the graph because it had two separate pieces or rules for the function itself. Okay, now we're about 30 minutes in. We've got one more topic to cover. I want you to pause, take a break, get something to drink, take some deep breaths, and then come back and talk about difference quotient with me. Now, the difference quotient is kind of like the slope, except a slope is for a straight line. Difference quotient you can use for any kind of a curve. Like right here, we got this funky curve. The difference quotient gives us the average rate of change between two selected points. Now, you're not going to have to define this for me. You're not going to have to even memorize the formula for the difference quotient. You just have to know how to use it. This shows me, okay, my graph is this curve right here. You can see that if I'm decreasing here. If I were to pick these 2 points as my x values, my difference, my rate of change between those is negative. When I turn here, it's positive, and like right here it's super steep, and here it's more flat, but it's positive. The difference quotient changes depending on which x values I pick. But I'm going to pick one starting place, one x value to start with, and then I'm going to move over so far, h units, it doesn't matter. I pick a distance to move over, and then I have another x value here. So whatever this was, it's plus h. So that's my input, x, and then x plus h. So for example, if this were 2 and I moved over 5 units, the second x value would be 7. Don't have to worry about that, but it's just an explanation. And then the y values, we've got the y value here where I have x, and then I've got the y value or the function value where I had x plus h, however far I moved over. And that makes sense of why we do what we do over here. So we've got that function value we stop at, x plus h. We subtract from it the function value, the y value we started with, f of x, and then we divide out that distance we moved over. We divide out h. This is my difference quotient. You don't have to memorize it. I'm going to give it to you when you have to use it. You must be able to use it. Now, using the difference quotient is really just a matter of order of operations, okay? We've got 2 pieces of information going on in the numerator. We've got one function value, we subtract another function value, we divide by h. The thing that throws us is that we've got a lot of variables going on when we're doing difference quotient. So we have to practice with those variables. Okay. We're going to identify the type of equation, use the difference quotient to find the average rate of change so that between any 2 points we know what it would be. Now, number 1, what type of function is this? If you need to, you can pull out your parent function sheet. It's not the parent, but I've just got an x there. It's not being squared, cubed, anything. And when I look through my functions, I see the one with just the x. Well, that's a linear function, so it's going to be a straight line. Straight line has a slope. So I can simplify this. My slope's going to be 3. That's what I'm looking for. But we're going to work through and practice with our difference quotient, knowing that this is a linear function. So it's going to simplify to give me a constant. Okay. Now, my denominator for my difference function is h every time. It's over h. My numerator has 2 pieces of information. The first piece is I take out whatever x I have and I replace it with x plus h. So I'm going to take out that x and I'm going to replace it with x plus h. That gives me 3 times x plus h plus 2. Okay, I took my function, replaced x with x plus h. The rest of what goes in my numerator is to subtract the original function. Now when I subtract the original function, I have to subtract the whole thing, so it goes in parentheses. So I subtract parentheses the original function, 3x plus 2. First piece, I replaced any x's with x plus h. Second piece, I subtract, in parentheses, the whole function. Okay. Let's go to our next step. Next step, still all over h. Order of operations in our numerator. For the green part, this first part, multiplication distributes. So I have 3x plus 3h, and then I've got plus 2. For my second bit, again, multiplication distributes across the parentheses. Think of this as a -1. I'm multiplying inside. it changes the sign on both of those terms. Now, after you've used your order of operations to kind of clean up this numerator, when you're looking at this second rational expression, you should start to see that you have a lot of opposites, pairs that add to 0. Something in its opposite adds to is something that adds to 0. For example, positive 2 and negative 2 add to 0. That's a pair of opposites. Additive inverses. Do you see another pair? Right there. 3x and negative 3x add to 0. So all I'm left with is 3h. And then I want to simplify. Anything over itself is just 1. And this simplifies to be 3. My difference quotient here is 3. It is a constant only because I have a linear function. And a linear function, a line, has a constant slope. Let's practice again with number 2, h of x. H of x is not linear. If you look at your parent function, I've got this x to the second power. That's quadratic. The graph is going to be a parabola of some shape, size. It does not have a constant slope. In fact, part of it's negative, part of it's positive. Down here it's really flat. Up here it's really steep. So it's going to depend on which x values we were to pick what the difference quotient would be. Okay, so let's start out. We're using our difference quotient, our formula. It is always over h. Always, always. Then in my numerator, I start by taking my original function. Wherever there's an x, I replace it with x plus h. I have x in 2 places. So for both of those, I replace it with x plus h. Note the parentheses, they matter. Parentheses are important. And then the second part of my difference quotient is to take the original function and I subtract that original function. I subtract the entire function. So I've got to again have parentheses, and I take my original function and I stick it inside those parentheses to be subtracted. Here's where our order of operations is important. Now we know that our denominator is just h. I need to start by squaring this binomial. That means I'm going to FOIL that, multiply x times h times x plus h, x plus h times x plus h. Then I have a minus 2 to distribute inside that set of parentheses. So negative 2x, negative 2h. And then the second bit, it's like that negative 1 distributes inside. It's going to change the sign on both of those terms. So negative x squared plus 2x. Now, before we clean anything up, we need to FOIL this. X plus h times x plus h. So I'm going to go ahead. You could have done this as side work. You could change it right there and make some adjustments, but I don't want to confuse anyone, so I'm going to go ahead and rewrite the whole thing. This x plus h times x plus h, when I FOIL that, x times x is x squared. Outside is hx, inside is hx, so there's 2 of those. So plus 2hx, and then h times h is h squared. And then I already had minus 2x minus 2h and minus x squared plus 2x. So this to here, I FOILed my x plus h quantity squared. You can absolutely go straight from here to there. Just don't forget that when you multiply a binomial times itself, it gives you 3 terms. Alright, next go. I want to pair up my additive inverses. Find the things that add to 0. Well, I've got a positive and a negative x squared. That adds to 0. I've got a positive and a negative 2x. Negative 2x, positive 2x. Add to 0. So what I'm left with, I've got 2hx plus h squared minus 2h. None of those are like terms. They cannot be combined, but they all have an h in common. So I want to simplify this rational expression. I can think of it as factoring an h out of all three of these, or I can write it as three separate terms, say 2hx over h plus h squared over h minus 2h over h. And I can split it apart and look at all three separately. Anything over itself is 1, so that's 2x. One of those h's cancels out, plus h. Anything over itself is 1, minus 2. That's my difference quotient. If I went here, remember I said you could factor out the h. I could have said h times 2x plus h minus 2 all over h. And then those factor, and I'm still at the same point. So you're going to get to this value when you simplify all the way. Now again, linear function, constant slope. This was a quadratic function, parabola, not a constant slope. So my difference quotient tells me that it depends on what x value I start with and how far over I move as to what the rate of change is going to be.